Hello. In this video, I'm going to introduce two key formulas of probability theory. There are two very basic and very important formulas in probability. If you understand these well, you can prove many other formulas. Most of the problems in Chapter 2 of the Stochastic Processes book can be proven using these two formulas. So if you understand these two, you can do most of the exercises. Right, first some definitions. Consider a sample space or state space. The letter that is often used for that is omega. Omega is the set of all possibilities. Possibilities means possible outcomes. Each of those outcomes will have a probability. Now, examples of state space include the set of possible outcomes of an experiment. An experiment is something that you can do repeatedly. For instance, you can toss a coin repeatedly. The possible outcomes of one coin toss are heads and tails. So my sample space in this case is h, t. If I throw one dice, the possible outcomes are 1, 2, 3, 4, 5, and 6. So this set is my sample space or state space. I could choose a random student in the class, and I can list the possible outcomes by listing the names of the student that I could possibly choose. The possible outcomes of choosing a random number between 0 and 1 is any real number between 0 and 1. So this is also a state space under this experiment. Another experiment could be the outcome of a random walk starting at 0. Let's try to list some of these outcomes. Now, in fact, a random walk is an infinite process, so there would be an infinite number of possible outcomes. So let's just look at the outcomes of the first 4. Okay, the first one will be 0. So let's consider all the outcomes where the first one is 0. Now, the first step could either be to 1 or to -1. Let's take first the case where the first step is 1. The second step could either bring me to 2 or to 0. Let me consider first the outcomes that the second step takes me to 2. If I'm at 2 at the second step, at the third step, I would either go to 3 or back down to 1. So this 0, 1, 2, 3 and 0, 1, 2, 1 are the only two possibilities of 4 steps when the first 3 steps are 0, 1, and 2. Now, I put ... here to indicate that there are many possible subsequent sequences. So I'm not listing all the possible outcomes, but I am listing possible outcomes for the first 4. There are many, many subsequent possible outcomes. So as I said, this state space is infinite. So the first 2 give me all the possible outcomes where the first 3 are 0, 1, and 2. Right. So as I said, when I reach 1 here, I could either go to 2 or to 1. As I said before, if I go from 0 to 1, the next possible step can either take me to 2 or to 0. Now I've already looked at all the possibilities where I go to 2. Let's look at all the possibilities where I go to 0. That would be 0, 1, and 0. Right? So if I reach 0 on the second step, on the next step I can either go up to 1 or down to -1. So these two give all possibilities for the first 4 steps, given that my first 3 steps are 0, 1, and 0. So we have looked at all the possibilities for the first 4 steps if the first 2 steps are 0 and 1. We can go 0, 1, 2, or we can go 0, 1, 0. If we go 0, 1, 2, we can go 0, 1, 2, 3, or 0, 1, 2, 1. If I go 0, 1, 0, I can go 0, 1, 0, 1, or 0, 1, 0, -1. So these are all the possibilities for the first 4 steps if my first step goes from 0 to 1. But I could also go from 0 to -1 on my first step, right? Because I could step to the left, which would take me from 0 to 1, or I could go to the right, which is 0 and -1. Now here we can use a symmetry property. any random walk outcome, if I take the negative of each value here, that's still a random walk outcome. In other words, if I have a random walk where I take steps left, right, I could reverse those steps, right, left, and still get a random walk. So here I have 4 more possibilities where I reverse all of these steps. Instead of 0, 1, 2, 3, I have 0, minus 1, minus 2, minus 3. Instead of 0, 1, 2, 1, I have 0, minus 1, minus 2, minus 1, and so on. So this gives me 4 different possibilities for the first 4 steps of the random walk. And again, this is not listing all possible outcomes of the random walk because there are many, many possibilities for subsequent sequences. Here I've begun to list all of the outcomes by listing the first 4. Now notice how many possible outcomes there are. There are 8 outcomes. If I wanted to do the first 5, you can imagine how I can do that. If this is the first 4, then the 5th place, there are 2 possibilities. If I go 0, 1, 2, 3, the next number would either have to be 4 or 2. If I go 0, 1, 2, 1, the next number would have to be either 2 or 0, and so on. Right? So if I listed 5 steps of the random walk, I would have 16 possibilities. But my entire state space for random walks is infinite. It's not possible for me to list all the steps of all the random walks. So in probability, we often use ... when we're dealing with infinite sets. All right, so we often use diagrams to represent what's going on. So in diagrams, omega is often represented as a box, something like this. This type of diagram is also called a Venn diagram. All right, now, let A1, A2, up to AN be subsets of omega such that the sets are pairwise disjoint. That is, no 2 sets intersect. And the union of all sets is the entire set omega. So I can give a diagram of some example. I'll draw my omega again. So here's my omega. And then I can divide this into different subsets. Okay. So this could be A1, A2. I'm just giving an example. 3, A4, A5. So you can see that no 2 of these sets intersect. There's no overlap between A1 and A3, for instance. No overlap between A3 and A5. The union of these sets is all of omega because they divide up the entire set. So such a collection of sets is called a partition of omega. You may have seen that in other classes. Now let B be an event. An event just means a subset of the state space. So here, let me draw B. B would be something like this. This could be an event B. Then we have this key formula, which is called the conditional probability formula. The probability of this event B is the probability of B given A1 times the probability of A1 plus the probability of B given A2 times the probability of A2 plus ... So I'm going to do A3, A4, etc., and so on, up to the probability of B given AN times the probability of AN, where the probability of B given AK is the probability of B within the set AK. Okay. This is also called the conditional probability of B given AK. All right, so this is a large formula. It may be difficult to understand. Now let's give an example. Consider a set of male and female students divided into 3 classes. Okay, so here is my example. Let me go ahead and draw my omega. Okay. And I have 3 classes. I'll call them A1, A2, A3. Okay. This is A1, this is A2, this is A3. Okay, and I have male and female students. I will denote my male students with X's. Okay, so 3 male students there, 5 male students there, students, and 2 male students here. And then I have my female students. Okay, 4 female students there. Let's say there's 7 female students here. I'm just giving an example, and let's say there are 2 female students here. All right. So in my diagram, A1 represents class 1, A2 represents class 2, A3 represents class 3. B is the event that a randomly chosen student is male. So if I wanted to show what B is the set including all of the male students. So this is my set B. So I want the probability that a randomly chosen student is in set B. Now, one way to find this answer directly would be to take the number of male students and divide it by the total number of students. So the number of male students is 3 plus 2, 5, plus 5 is 10. The total number of students is 10 plus 4, 14, plus 7, 21, 22, 23. 10 over 23. Okay, so that's one way to show it. Now we can also use the formula. The formula says that P of B equals P of B given A1 times P of A1 plus P of B given A2 times P of A2 plus P of B given A3 times the probability of A3. Now that's my formula. Let's figure out all these terms. Probability of B given A1, let's figure out what that is. That's going to be, well, there's 3 males in the class, and that's out of 7. The probability of A1, well, there's 7 in class A1 out of the total number of students, which is 23, right? Okay. We counted before, the total number of students is 23. All right? Now I want the probability of B given A2 times the probability of A2. Well, let's look just at A2. How many males in A2? Well, there's 5 of them. But I want the probability of B given A2. I want to do 5 divided by the number of students in A2, which is 7. Okay. And then here I want to get times the probability of A2. Well, there's 7 students in A2 out of total number of 23. Okay. All right. Now finally, let's look at the last one. Probability of B given A3. Well, there are 2 male students in class A3. And that's 2. The total number of students in the class is 2, 3, 4, 5, 6, 7, 8, 9. Okay. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then here we have times 9 over 23. Okay? Now let's work this out and see if we have the same thing. This gives us, well, the 7's cancel, so I get 3 over 23 plus 5 over 23 plus 2 over 23. And that gives me 10 over 23. Okay? So these two agree. I do have the correct answer. Okay? Now, you might wonder, why do the problem in such a complicated way when we have a much easier way? Well, it turns out that sometimes you have this information, but you don't have the entire information. This is breaking up the large problem into some smaller problems. So that's the first key formula. So I give an exercise here. Suppose we have the following numbers. The population of Kano State is 16 million. The percent vaccinated against COVID is 5.5%. I actually looked these numbers up on the internet. The population of Lagos State is 11 million. Percent vaccinated against COVID is 7.5%. The population of Kaduna State is 8 million. The percent vaccinated against COVID is 3%. So choose a person at random from one of these three states, where the probability of choosing any person is the same regardless of what state he/she is from. Okay. So that means since there's 16 plus 11 plus 8, what is that, 24, 25, 35 million people in these three states, the probability of any particular person is 1 over 35 million. And that's the same probability for individuals from Kano State, Lagos State, or Kaduna State. All right? So, find the probability that the person you have chosen is vaccinated against COVID. Okay? So, use your conditional probability formula to find this probability. All right. Exercise 2. Let omega be the set of all possible outcomes of a random walk. So this is what I discussed above. There's an infinite number of possible outcomes. Let xn be the position of the walk after n steps, where x0 is 0 with probability 1. So this, again, is a random walk started at state 0. I'm going to define a quantity q small n big N as follows. Q of 0 comma n is the probability that xn is equal to minus n. Q1 comma n is the probability that xn equals minus n plus 2. Q2 comma n is the probability xn equals minus n plus 4. Qnn is the probability xn equals n. Now you may wonder, why am I skipping 2 each time? Well, look up here. You can see what's going on if you look up here. After 3 steps, what are the possible outcomes for the third step? Well, the smallest one is minus 3. The largest one is 3. The other 2 possibilities are minus 1 and 1. So after 3 steps, the possible outcomes are minus 3, minus 1, 1, and 3. And if you look at how random walks work, this is a general rule. After n steps, the smallest possible location is minus n. The largest possible location is n. And the possible locations have increments of 2. It's not possible to have minus n plus 1, only minus n plus 2. This is true in general. Okay. All right. So question A. Express the probability that x2 equals 0 in terms of q10 and q11. So what I'm saying here is that I want the probability that the random walk is at position 0 after 2 steps. And I want to express that probability in terms of these 2 values. I don't want the value of x2, probability x2 equals 0. In fact, that's 1/2. But I want to express this in terms of this and this using the conditional probability formula. Now, second question, express the probability that the random walk is in state 0 after 4 steps in terms of Q03, Q13, Q23, Q33. All right, so remember, the first index runs from 0 to n if the second index is n. So in fact, there are 4 Qs for Q03, Q13, Q23, Q33. All right, so these are 2 particular examples. Question C, supposing n is odd, express the probability that the random walk is at 0 after n plus 1 steps in terms of these values. So let me emphasize, in order to do this, I want to use the conditional probability formula. Using the conditional probability formula. Okay? So I've introduced the first key formula of probability that involves conditional probability. In the next video, I'll introduce the second key formula.